Now we're going to introduce a new topic, and we'll continue with this next week as it's directly related. And this gets into some really fundamental stuff. And we're going to be talking about something we're really familiar with, at least in principle, but there's usually more to the picture. So our everyday word here, momentum, and this was expressed by Newton by one of his laws, saying that an object in motion will continue to stay in motion unless acted on by some outside force. Likewise, an object at rest will tend to stay at rest unless acted on by an outside force. So the fact that an object continues to move in a particular direction once it's going, so there's a mass and it's got some velocity v, it's going to just keep going unless a force acts on it. This is called momentum. It has you can assign a value, you can assign a value to momentum, a number to momentum, and the equation is very simple. P equals mass times velocity. P is the symbol for momentum. I don't know why, it just is. Probably because m is mass, so they had to come up with another symbol. So momentum equals mass times velocity, and just to clarify, v is a vector, right? Velocity is a vector. So Andre, do you think momentum is going to be a scalar or a vector quantity?
It's going to be a vector quantity.
Right, because you have mass, which is a scalar, times a vector, so you've got a vector. So this object here will have, let's say it weighs 2 kilograms, and it's moving at 5 meters per second at 30 degrees. So P is going to equal 2 kilograms times 5 meters per second. So it's going to equal 10 kilogram meter per second. And again, the angle is simply 30 degrees. So that would be the momentum vector. The units for momentum are simply kilogram meters per second. They're not newtons, they're not angstroms, they're kilogram meters per second. Now, there's a lot of interesting things that can be said about momentum, but we need to talk about what the nature of momentum is. Or another way of saying it is what causes momentum. You could say it that way. And the answer to that is extremely interesting. Let's talk about it a little bit. So, first of all, you're simply assigning a number to an object in motion by saying that there's some quantity, we're going to call it momentum, and it equals the mass times the velocity. Now, let's pause this for 1 second. Okay, so now to talk about momentum, before we can get into it too much, we've got to talk a little bit more about mass itself, because the general everyday understanding of mass is simply that mass is equivalent to an object's weight. This is not true. Let me explain. Let's say you have an object, and on Earth it weighs 10 kilograms. What you're saying is that it might weigh 10, you say that it weighs 10 kilograms, but the force due to gravity equals the mass times the acceleration due to gravity. Sorry, that should be a g. So the force due to gravity is 10 kilograms times 9.8 meters per second squared. So the force due to gravity equals 98 newtons. Do that right? Now you're hearing my own thoughts. Okay. Force equals mass times gravity, the acceleration due to gravity. So that's on Earth. You take the same 10 kilogram object to Mars or the moon, for example, and the acceleration due to gravity is much less. So let's do the same thing on the moon. So here's our 10 kilogram weight, and the force due to gravity is going to be 10 kilograms, and I forget exactly what it is on the moon, but the acceleration due to gravity, let's just say it's 1 meter per second squared. So now the force due to gravity is only 10 newtons, right? The object has not changed. However, its weight has changed. Weight is simply the way you experience mass in a gravitational field. If that gravitational field is stronger, the object will have more force due to gravity. If it's weaker, it'll have less, such as on the moon. Yes?
Weight is only relative to the amount of gravity in a certain place.
Yes, exactly. The weight is what you experience because of gravity. Now let's look in outer space. You can still have your same 10 kilogram object in outer space, and it doesn't weigh anything. So what's going to distinguish this 10 kilogram object from, say, an object that weighs 1,000 kilograms? And it may not be their volume. Maybe, let's say the 10 kilogram object is made of styrofoam, and you have a thing of uranium that weighs 1,000 kilograms, but they're the same volume, and they're in outer space. How would you figure out which one has more mass? Anybody have an idea? How will those objects seem different to you? Say you're a spaceman. Here's our spaceman. He's floating around in space. Yeah. So how is he going to distinguish which one has more mass, Andre?
Well, if he pushes on them, there will be a difference in the force that's exerted back onto him if he uses all his strength. For example, it's a lot easier for him to push 10 kilograms than it is for him to push 1,000.
Exactly. If he tries to push the 1,000 kilogram weight or tries to throw it, he's going to go flying backwards he's going to go backwards more than that one's going to go forward. If he tries to throw the 10 kilogram one, the 10 kilogram one will go forward pretty well, and he'll just kind of stay in the same place. We experience this on Earth when you try, let's say you can experience it pretty easily. Imagine 1,000 pounds of something on rollers and 10 pounds of something on rollers. You're hardly going to be able to move that 1,000-pound thing. But for example, the other day we were moving the car in the shop, right, guys? We all had to push on the car to get it to go, and it was on rollers because its mass is so large. That's a way of experiencing this in everyday life. So mass is something other than just the weight that you experience from an object. So that being said, we can kind of get back to this idea of momentum. Momentum is an expression of a quantity that has to do with the mass of an object and its velocity. Now, it seems that I'm kind of talking in circles, and the reason is this. In reality, you can learn all about momentum. You can learn all about how you calculate things with momentum, because there's a lot you can do with it. But in reality, the fact that you say an object has momentum is a tautology. Who knows what a tautology is? Thea.
It's an argument that you support by using the thing you claim is a conclusion.
Exactly. It's circular reasoning. All I'm saying by saying that something has momentum is I'm simply stating that an object in motion will continue to stay in motion. Okay? And I'll explain this a little bit more. We have to stop this one because we're going to run out of time on YouTube, but we'll do one more lecture after this and talk about this a little bit more.